Please pause the video and take a moment to read this important safety message.
Hey, welcome everyone. Mark here at Blue Glow Electronics. Today, oscilloscopes for audio bench work, safety and precautions. Okay, part 2 in our Oscilloscope for Audio 101 series. If you have not watched part 1, please go do so. There are components in it that we will reference in following videos, including today's. It also gives you a good breakdown of this series. So with that, onward. All right, just a little context on why I even made this safety and precaution video, okay? In audio work, you will be around high voltages. There's really no way to avoid it, okay? Even in a solid state situation, you have your AC mains voltage that comes into the unit and then feeds the power supply. Here in the United States, that's 120 volts, okay? That's enough to kill you if not handled properly. In other parts of the world, it can be as high as 240 volts, so even more dangerous. But typically your solid state gear will come, you got the AC mains coming in, it'll feed into your power supply, and then it typically gets lowered down for components within the solid state piece of equipment. Tube gear, on the other hand, it typically gets stepped upward. So you're going from this 120 volts in to up as high as sometimes 600 volts or more. Now, in audio gear, 600 volts is not all that common. 150 volts to somewhere around 450 volts is much more common. But every once in a while, you do run into some gear that runs on up there 600 volts or more. Either way, 150 to 450 volts, definitely enough to kill you. All right, it's also all about the ground, and we're going to talk about that more here in just a minute. But having said all these kind of warn you, scare you things, having said all that, you can operate around this equipment safely, and hopefully what we will show you in this video is how to do so. All right, great question for you here. Which one is the killer, current or voltage? Well, the answer that they will teach you in textbooks, it's really current that kills you at the end of the day. But voltage does play a role into this. Remember back to Ohm's law, there's always some trade-off between voltage, current, and resistance, and we'll talk more about that in the next slide here. All right, this next little table shows you a little bit of what it takes to actually kill you or hurt you as it relates to voltage and current and whatnot. So, let's say you grabbed a hold of something in a circuit, right? And it had 1 milliamp of current. Well, if the resistance between, what you grabbed onto and ground, because remember, for something to hurt you, you have to complete a circuit, okay? So maybe it's your feet touching the ground. Maybe you're standing in a pool of water. If maybe you're standing in a pool of water barefooted, you don't have a lot of resistance between you and ground. So whatever you grab a hold of is going to flow right on through you very quickly. Whereas maybe you've got some tennis shoes on, right? Some rubber bottom tennis shoes, and you've got a whole lot more resistance here between you and ground. It may take more voltage for that current to find its way through you, in other words. But here at 1 milliamp of current, you feel it a little bit, maybe a little tingling sensation. If you've ever stuck a 9-volt battery on your tongue, you felt that tingling sensation, that might be what you get out of it. Up here at 15 milliamps, you start to, this is about the most you can handle before you start withstanding some injury here. You get up 15 to 20 millivolts, all of a sudden you get into this place where you can't let go, okay? So, and that can happen as low as 10 volts if you're standing in a puddle of water, barefooted. But, if you're rubber shoes on, insulated, whatnot, it may take a lot more potential to cause that happen here. And this is just an Ohm's law equation that's going on here. But you get up in the 100 to 300 milliamps, and the B+ circuits we build in a lot of our tube amps are in this range. This is the same as hooking a defibrillator up to you, okay? Fatal, right? Respiratory functions, things of that nature. You get up here into the 6 amp, and it's bad stuff, okay? Let's look at the next slide. All right, the next slide or two are probably the most important in this entire video, so please pay attention. All right, see this little picture I drew down here of this guy? Okay, forgive my artistic skills as well. It's a top-down view. This guy's working on, let's just say it's a guitar amplifier, okay? And he's got his right hand bent over here, and he's grabbed a hold of a black oscilloscope probe, and he's probing around down inside this guitar amplifier trying to look for the audio signal, okay? And what's he doing? He is doing the most logical thing known to exist, and that is to use your left hand to steady the piece of gear that you're probing in with your right hand, right? Maybe you want to turn the amplifier a little bit to make it easier to get your probe into where you're going. So you got your left hand holding on to the chassis. Well, if we know anything about electronics at this point in time, what does electricity do? It completes a circuit and it will try to find the fastest and least path of resistance to ground, okay? And what you don't want to do is turn your body into that. With grabbing the left side of the chassis with your left hand and probing around over here, if that person's finger accidentally touched B+, okay, you may create a new circuit that flows right up your right arm, right through your chest, right down your left arm, and right back to chassis ground. You may become the lowest resistance to ground in that circuit at that moment in time, and you're going to carry not only the current through you that is in that circuit at that point. And if this is B+ in a tube amplifier, we're right back to maybe 200 milliamps flowing through you. Remember what 200 milliamps does back here? Ventricular fibrillation, okay? Fatal if continues, right? It's not what we want. Never do this, please, okay? Always remember, keep that second hand away. Don't grab the chassis. Sit on it if you have to. Okay, let's say you play by the rules and you don't keep your left hand on that chassis, okay? You know, one thing that'll happen, if you get shocked with just one hand, okay, so your other hand's not grounded to the chassis, you've likely got on rubber shoes, you're sitting in a leather chair or a cloth chair, you don't really have a good path to ground, okay? So getting shocked with one hand will likely hurt, but it won't kill you because you don't have a path for all this current to flow through your body to ground, okay? In my personal experience, many, many years on the bench here, it is incidental contact with a component on the other side of your hand. In other words, you've got an oscilloscope probe, or maybe you've got a multimeter probe, and you're down in there, and the right side of your hand, you know, your pinky, the back of your palm, that's usually what gets you. You accidentally touch something that you didn't mean to focus on, and it gets you, okay? So that's easy to solve. Take your time, be diligent, pay attention, not only to what you're probing with, but the other side of your hand and whatnot. Okay, a little concept I'm going to need you to grasp, and that is that AC voltages, right? This is whether it's sinusoidal, square wave, triangle wave, or just audio waves. When you put them in a circuit where there is a DC voltage on that same circuit, those two things add to each other. They're cumulative, okay? I'm going to give you an example. Here is a 300 in the black line, 360 volt peak-to-peak AC signal here, and it is hovering around a reference point of 0 volts here, okay? In other words, ground in most amplifiers. So we go on up 180 volts, back down to 0, minus 180 volts, back to 0, 180 volts. So the most this amplifier, if you were trying to measure this with an oscilloscope, it would see from 0 to plus 180 and 0 to minus 180, okay? So this oscilloscope needs to be able to handle, here in this case, 180 volt peak, right? Well, what happens if we add to it, somewhere along the way, we added a DC voltage of 180 volts or 200 volts or whatever it is. All of a sudden, this AC voltage is no longer kind of oriented around ground. Now it's oriented around this 180 volts. So we're not going here from 0 to 180 anymore. We're going from 180 to 360, back down to 180, back down to 0, back up to 180, back to 360. So now we've got to be able to deal with a peak of 360 volts because we've got this AC voltage component added to it. All right, so most oscilloscope inputs will be rated somewhere labeled on the unit itself or maybe in the owner's manual. But this is my 2246 over here on the bench. And if you'll notice the label on it right here, what does it say? It can roughly handle anything lower than a 400 volt peak, okay? And that's what it's kind of saying here. Check your scope for your specifics. And you've also got to notice here, there's two buttons here. There's an AC coupling button and a DC coupling button. Okay, and you may wonder, well, what does that do? Well, if that 400 volt peak was riding on top of, say, a 200 volt DC signal, all of a sudden I've got 600 volts going into this oscilloscope. Bad things will happen to my oscilloscope. But I can block the DC component simply by putting the scope into AC coupling. Click it on this, which in essence what it does is, in series with the input of this, it puts a little coupling capacitor to block the DC rated at 400 volts. So it can handle up to 400 volts DC that it's blocking. All right, so then we get rid of the DC component, and now I'm back to I can handle a 400 volt peak AC signal going into this oscilloscope. So that's why we use the AC coupling most times when working on audio gear. We want to get rid of any DC component coming in, because really what we're trying to look at is the AC component. Looking at a DC component is pretty boring. All you see is a flat line and you measure it and you go, okay, oops. All you do is look at a flat line, you measure it, 1, 2, 3, 4, okay, it's 180 volts, right? But an AC signal, that's where you can tell really what's going on. Is this half the signal, symmetrical with this half the signal? Things of that nature. So you might say to yourself, well, heck, this is easy. I'll solve all that. I'll just get me one of these 10x probes. That way it divides everything going into my oscilloscope by 10 times, right? So give you an example over here. This is a 10x scope. Most scopes have a 10x setting. There's a little flip switch on it. One side will say 1x, the other side will say 10x. If you have it on 1x, whatever you're measuring, it directly ties that voltage into the oscilloscope. And the other side here would, if you flip it that way, it would reduce it by a factor of 10x. So you may think to yourself, well, heck, if my oscilloscope says 400 volts peak, and I just put a 10x scope into it, well, that's easy. Now I can measure 4,000 volts. Unfortunately, it doesn't work like that, okay? These scopes are not capable of handling that type of voltage, okay? The voltage divider inside of this has components that can't handle those kind of voltages. So in most cases here, you're limited somewhere around the voltage going into your scope. I actually looked this one up on Amazon, and it says it can handle about 600 volts. So you might get by with a little bit more by using your 10x probe. You're not going to get 4,000 volts feeding into your probe, into your scope, and measuring it. You will fry some things along the way. So there is an easy solution for all of this, and that is to use what is called a differential probe, okay? Let me go back here for a second. This probe right here, if you'll notice, has a little ground clip on it, and you can use that or you can not use that, and we'll talk more later about this. But if you don't use it, all it does is reference back to ground here on this BNC connector, which then hooks to the outer part here plugged into your scope, which is then, guess what? Tied back to earth ground. So when you're measuring the end of the probe here, you're measuring one voltage. It's then referenced against the outer lead here, which is tied back to ground or earth ground, right? Well, a differential probe, it kind of defeats all that. And it does that by having a differential amplifier inside of a little box here. And instead of one output, you get two outputs. You get two probes here, right? One of which you might want to use an alligator clip or something to clip onto the ground in the amplifier. And then the other one you can measure using like a scope probe here or another alligator clip. You measure parts of your circuit at that point. And what it does is it measures the difference between these two terminals here coming out of this amplifier, and not between the tip of this and the oscilloscope ground. Very different setup here. So then what gets sent out of this, there's some circuitry in here. What gets sent out of this is then a much smaller signal feeding out back to this that is not referenced back to this right here. In other words, this probe that's ground here is not directly tied to this. There's usually 4 or 5 mega ohms between these two here. So not totally isolated, but for all intents and purposes, pretty darn close. So then you could use this device, and if you could read it and you can't, it'll say right here it's 1,000 volts that it can measure between these two probes without damage, okay? So that would let you get inside your amplifier and click the ground here on ground and click this and measure anywhere inside of that. And then there's two buttons here. One is a 50X and the other is a 500X, okay? And we'll talk more about that in a little bit. In other words, it's a big divider. It's taking that 1,000 volts and maybe sending it out as either 20 volts or 2 volts into your oscilloscope. All right, well, you're like, okay, well, cool. That lets me measure anything up to 1,000 volts inside of an oscilloscope. I'll just always use a differential probe. It's clunky. The bottom line right here, I said it, the downside, they are somewhat clunky. Now, there are some other scenarios where these things are great. Maybe if your amplifier has differential outputs, or maybe if you're using it in bridged mode, okay, where you're not referencing back to ground. These things are phenomenal to have, and I use one from time to time, but I don't use it all the time because you got to plug this into your oscilloscope. You got this little box laying on the bench, and oh yeah, by the way, that box has circuitry in it that needs power. So you then got to plug in a USB plug here, and you've got to power this unit from somewhere. Modern digital oscilloscopes typically have a USB port in them you can power this off of. Older scopes won't. You'd have to have some kind of wall wart that you powered this off of. It just gets kind of clunky on the bench is the bottom line. All right, getting back to practical bench experience here, 98% of the time, i.e. other than 2 or 3 times a year, I usually pull out a normal scope probe, and it's just a normal 1X, 10X, and I don't use a differential probe, and this is why. Okay, in solid state receivers, amplifiers, preamps, you name it, the highest voltage you're typically dealing with is the AC mains coming from your wall. And typically you don't really care to measure the AC mains because you know what it is and you know it's probably not perfect, but it's decent, right? You care about what's on the other side of the power supply that's feeding your components way more so than you do what's coming in from the wall, right? And typically the other side of the power supply, these things get stepped down a good bit, anywhere from 5 volts to 70 volts, right? So it's pretty safe probing around inside of a solid state unit other than maybe the AC mains area. And that, if you get good at electronics, you'll figure out where that's at and you'll just kind of avoid that area, okay? In tube gear, right? It's just the B plus you're really worried about. Those get stepped up in the power supply to voltages ranging from maybe 100 volts to 600 volts. But we can measure those things with a digital multimeter if we need to, right? There's not a lot of times that I actually measure the B plus with an oscilloscope, okay? I usually measuring the B plus with a digital multimeter. By the way, digital multimeter, it's got a battery in it. It's not referenced back to earth ground in any way, so it really, you measure a lot of voltage with a digital multimeter and not have a lot to worry about. So really, we can follow the audio signal through an amplifier and avoid the high voltages that would cause our oscilloscope problems. And because of that, 98, maybe even more % of the time, I can get by with just a plain old oscilloscope probe. All right, when would you definitely want to use a differential scope probe? One, you got a bridged amplifier set up. So you got a stereo amplifier, but it has some special features that'll let you bridge the 2 stereo outputs together into a mono output at twice the output power. Typically you're bridging those together and part of them then is not referenced to ground, and you're going to want to avoid probing those with a probe with a lead that is referenced to ground. You can fry one of your outputs that way. So there you'd want to use a differential scope probe. Similarly, an amplifier that just by nature has differential output circuits in it. Older hot chassis tube gear, great example, old phonograph units that like fold up in cabinets, or you carry them around, little record players you'd open up that would be tube based. Those things are notorious for having what we call hot chassis to them. In other words, 2-prong, and one side of those happens to be the chassis of the unit, which makes it hot. I try to avoid those units at all costs, but those you would definitely want to use a differential probe. Hey, when you truly do need to measure more than 400 volts AC, right? Maybe you need to measure 800 volts, got 800 volts on the plate here, and you want to be able to look at that. use it. And there's a few other special circumstances, but for the most part, this is it. All right, let's take a look at a schematic for a very common Marantz power board, the P800. It's used in several of their units, okay? But let's take a look at the voltages. So coming into this, you would have the 120 volts feeding into your AC mains, which would then go into the power transformer. But then the power transformer feeds this board, okay? So this is then feeding outward from this board where things get kind of rectified and whatnot, and regulated and sent on to the rest of the unit. Look at the voltages we're talking about. There's 42 volts here. There's 15 volts here. There's 31 volts here. There's 7 volts here. There's 36 volts here. There's 46 volts here, right? I'm not seeing high voltages that my oscilloscope can't handle with just a regular probe right here. So we're good to go on all solid state unit. I'll say all with a caveat. There could be something out there, but vast majority of all solid state units, just a regular oscilloscope probe, you're good to go. Other than those bridge scenarios, the differential output scenarios I mentioned earlier. All right, so this is the single-ended 807 amplifier we built with you guys a few years ago. This is the power supply section of it. Notice feeding in here, we've got 120 volts. We could measure that with a regular oscilloscope probe and a regular oscilloscope. Then we have 355 volts, 0 volts, and 355 volts. In other words, 355 volts here, 0 volts here, 355 volts here. We could actually measure each side of this individually with the regular scope. We just couldn't clip from here to here because then we're putting 710 volts into our oscilloscope. That would be a bad thing, okay? But then we go through here, the rectifier, we come out the other side of it, and what do we got? 405 volts sitting here, right, of DC with maybe a little bit of AC hum on it, so you might want to see that, okay? We probably get by with using a 10x probe and flipping it to 10x and measuring 405 volts right here, right? Then we could come over here and measure, we're down to 402 volts when you get on the other side here of this choke. On the other side of this resistor, we're down to 334. You know, we can probe around in here just fine with a regular oscilloscope, nothing special needed in here. And then if we go over here and we want to measure, so let's just say this is a different amplifier, but it happens to be the 807. I kind of drew a pink line here that follows the signal path through this amplifier. Typically you're using an oscilloscope not to look at DC stuff. It's not what they're made for. I mean, you can look at DC, you can see it's an offset, and you can see it's a flat line, and how flat is it? But it's not really what oscilloscopes were designed for. They were really designed to look at AC components. And so I could clip a lead here and measure the input of this amplifier and watch a little signal. I could watch it go through the potentiometer here and measure it over here on the other side. It's almost always safe to connect to the grid of a tube. And I'll tell you why here more in a minute, and you'll see. So I'm connected to the grid here of this first tube, and I'm watching the signal feeding into it. It's teeny, teeny, teeny. This is like less than a half a volt right here, okay? Then it goes into this tube here, and it gets amplified. Well, sitting right here on top of the tube, if I measured right here, then I would have B plus of 300 volts, plus whatever swings coming out of this. Maybe it's 20 volts going each direction here, okay? So I could be getting a 320 volt peak, but hey, even there, I'm okay measuring that with a regular oscilloscope. But I probably wouldn't measure it right here. Why? Because I could just as simply click on the other side of this coupling capacitor, and at that point, I have 0 volts DC, because remember, coupling capacitors block DC. And then if I measured it right here, then all I have is the 20 volt peak-to-peak AC signal. There again, it's the same as connecting to the grid of the following tube. Why do I connect to the grids of the following tube? Because I see what's feeding into them, and I know that typically we block the DC coming from the previous, segment. All right, so same thing. Signal flows in through here, out through here. If I measure here again on the grid of this tube, I'm on the other side of, forget the 334 volts, it's gone. It got blocked by this coupling capacitor. So then I'm sitting here maybe measuring, something like, I don't know, a 60 or 70 volt peak-to-peak swing, okay? Feeding into my 807 coming out the other side of it. Oh yeah, by the way, this signal right here is likely swinging all the way from like 0 all the way up to 402 volts or thereabouts, okay? Big swing here. Maybe you don't want to measure this right here on top of the plate. Well, it's simple enough. Just clip on the other side of here of the output transformer, which removes DC, by the way, and you're back down to whatever AC signal you've got on the other side of this. By the way, this thing is taking this large signal and it's doing a voltage conversion. At the same time, it's stepping down the voltage and up the current. On the other side here, you're probably measuring something like, there again, back to 15 or 20 volts coming out on this side. And you're able to watch the signal. So if I was going to measure this amplifier on the bench, I would simply click here on the grid of this tube and watch it. I would clip on the grid of this tube and watch it. I'd clip on the grid of this tube and watch it. I'd clip on the other side of the output transformer here and watch it. And I can watch my AC signal all the way through this amplifier and never touch any of this high voltage nasty DC that might get us out of range of what my oscilloscope can handle. We're going to go to the bench here in a minute and actually show you this. All right, before we jump off to the bench, I'm going to put this link down below. I would highly encourage you guys to go watch this. It's a 24-minute long video. It's Dave over at EEVblog. And by the way, this guy, he's forgotten more about electronics than I know, okay? He does it for a living and I don't, right? I do this as a hobby. But he does an excellent job here of talking about how to not blow up your oscilloscope, i.e., how to deal with this grounding stuff that can trip you up is what his video is really all about. And he does talk a little bit about differential probes and other things in this video. And he probably does a better job at it than I can. I'm going to do a super condensed version of it here. But if you want a really good story on it, go watch this video. All right, if you don't want to watch Dave's video, here's Blue Glow's super abbreviated version of it and not in near the depth that Dave goes into, but I'll give it to you anyway. All right, this is your house here. It's a little shack, I get it, but it's your house. And in it, you've got a box here, right? And that is typically called your service box, i.e. your power panel in your house, right? And then from that, feeding out throughout your house is typically Romex cable of certain sizes, depending on the length and the amperage, to feed outlets throughout your house, okay? And then typically coming out of this box, there's a ground bus in it. And that ground bus is tied outside into a copper rod driven, typically a zinc-coated copper rod, 6 feet into the ground or so outside your house. So it truly is ground. It's driven into what's called earth ground. And typically this earth ground is tied back in here. And here in the US, it is the green wire, okay? If you're working inside of something and you see a green wire, it's typically tied all the way back here to earth ground through these outlets, okay? So these are what your outlets might look like on the wall, and you got 3 prongs here in the USA, okay? One is ground, earth ground. Notice this? So if you plug in your little thing, that little round plug that goes right there, it goes back through the wall, goes back through this unit, it goes into this ground bus, ties all the way down, goes into this rod into the ground, okay? Similarly, with this one would do the same thing. Then you've got 2 other leads, okay? You've got the hot lead. This is where your AC signal rides on right here, this hot lead right here, okay? And then you've got the wide spade here, which is your neutral. And in almost all scenarios in the United States, this neutral wire back here inside of this chassis is tied back to ground as well. So it's the same as this ground here is, okay? And then this hot signal is kind of riding on top of that, okay? So typically neutral and ground are bonded together back at your service box here in the US. Probably the same in many other countries. So how might that create a problem for you? Well, if you'll notice your oscilloscope here, right? My nice little drawing of an oscilloscope, it's plugged into a wall outlet, right? Which then ties back to ground, goes back into your box, tied back to ground. Well, on your oscilloscope, these little B and C connectors, the outer portions of them are tied to ground, chassis ground on this unit, okay? Which guess what? Because chassis ground and earth ground are tied together, this all goes back to earth ground, okay? Not a big problem. assuming your amplifier over here that you're working on, that I've drawn here, right? Your power's feeding into it, goes in here to transformer, comes out of the transformer typically into some chokes and capacitors and whatnot. Then you feed B plus here into your tubes, right? And the other side coming out of your transformer here gets tied to chassis ground. And guess what? Your chassis is tied to ground. And then typically the chassis ground and the earth ground are tied back together back through this box. So that's a fine scenario. This is like 90+% of the stuff I do, right? I'm able to plug my scope here directly down here, clipped onto the B plus, and then I pick up my ground, not through the little probe here going into and tying to the amplifier. I pick up my ground via coming back out the ground of the amplifier, back through the wall outlet, back through the scope, back down to here. It works pretty well with audio signals. If we were working on RF equipment, doesn't work well at all. The long wire you have of your ground coming back through all this, through the chassis, through your wall outlet, coming back through, back down to your other piece of gear, there's a lot of problems that you will have with grounding loops here, basically, and noise on the ground that will make it hard for you to measure. But at most audio signals, not a problem. I measure audio signals all the time with nothing more than an oscilloscope here, plugged down in, clipping on to whatever I'm trying to measure in the amplifier without even using a ground clip on the oscilloscope probe. I'm probably picking up a little bit of noise, but usually when I'm troubleshooting, it's not that little bit of noise I'm worried about. I'm worried about signal distortion. I'm worried about, is my signal too low? Did I lose my signal somewhere along the way? So a large percent of the time you're okay doing this. And you can easily test this. All you got to do is get out a digital multimeter. Is the amplifier ground, in other words, your signal ground in your amplifier, and your chassis ground the same? So get a digital multimeter out, put it on continuity test, find the ground of the signal, test that against the ground of the chassis. If so, you're probably fine testing your piece of gear on the bench this way. Now, from time to time, you'll find a scenario where your audio signal ground and your amplifier chassis are not tied together, okay? If that's the case, you typically want to do two things. One, put an isolation transformer here in line within your amplifier. That way you're isolating the chassis ground here back from your scope ground here, okay? You're kind of isolating the ground between these two things. And sometimes you'll need a plug adapter. If your isolation transformer only accepts a 2-prong input, but your amp has a 3-prong input, you may need one of those 3-prong to 2-prong adapters I showed you in video 1. But in this case, then, you would be able to measure, and oh yeah, by the way, then you can use your little ground clip to clip down here in your amplifier and tie that back to your audio ground. Then you're measuring your signal against audio ground, and you're good to go. And typically these little clip-on leads here are 4 or 6 inches, something like that long. But if you're going to do that, typically you want to have an isolation transformer in play. One thing I would not recommend, some people will say, well, there's an easy way to solve for that, Mark. I'll just put my oscilloscope on a isolation transformer. That way it's always isolated from the earth ground, and I never really have to worry about it conflicting with the ground and the device under test here, the DUT. Well, that's not a good thing either, because then let's say you clip over here and you clip onto something, and maybe the place you clip is 200 volts. Well, you just tied back through this oscilloscope probe back down here. Now these little outer sections of the B and C connector are sitting at 200 volts. Well, if you happen to grab onto that and something else on your bench, you might become the shortest path to ground for 200 volts at however many milliamps. You might get shocked, potentially electrocuted. So it's not a good idea to isolate your scope, because there are parts of the scope, specifically these BNC connectors, that are exposed, and you want to keep those tied back to earth ground. So it's always safer to isolate over here on the device under test. Now, myself personally, I typically have the switch that I plug my device ender test in on my bench plugged into an isolation transformer all the time. Okay, it keeps this chassis ground from being tied back to this. But what it means then is I can't always just use a scope probe and pick up the ground coming back through all this, right? In other words, I have to use a lead connection. And sometimes, like on my 2246, it has a little ground plug on the front of it. I'll just run a green alligator wire down and connect it to audio ground. And yes, I get that that's a 3-foot long connector and it's longer than this. But for audio signals, you're okay. If we're talking RF, you're introducing a lot of problems in reading your signals. So, but for the audio world, pretty good leaving this isolation transformer in place all the time. Having said all that, it's time to go over to the bench and actually see some of this in action. Okay, we're over on the bench now, and what we've got here is our 2246 oscilloscope, and this could be at any oscilloscope. And I've just got an amplifier mounted here on the bench. And what I've done is I've taken the negative lead of my multimeter here. By the way, the multimeter is set to continuity test, and you guys know when you're on continuity test, if you touch the ends together, it indicates that you have continuity with little or no resistance with a beep. So I'm going to clip on to what is my signal ground. That's the bus ground inside of this amplifier. It could have been a star ground, but it is the signal ground. And what I'm going to do is verify that the signal ground here is tied to the chassis ground. Okay, so I'm just touching the transformer bolt that's going through the chassis. Okay, I'm touching another place up here where I've got a terminal strip mounted down and the powder coating removed. And you can see what that means is that my signal ground and my chassis ground are one and the same here. Okay, check this out. So coming down here, there's a green lead here going into the IAC connector down here at the bottom. And if I touch that, and it is tied right back to the chassis, which now means it flows out this cord into my wall outlet, back through the house mains, back to my panel box, where it is actually tied to earth ground. Now, at this point in time, I have my oscilloscope plugged into just using a 3-prong cord with the ground still attached. So watch this. I just attach to the outer of channel 2 here, and if I take this probe loose and touch the outer of channel 1, they're all tied back to earth ground. And if you'll notice here on my oscilloscope, there's also a little place right here where you could insert a lead, and it's actually marked with the earth ground lead. So what that means is I've got a single oscilloscope probe here, and this is one of those little $20 probes that I had shown you guys. I'm now able to probe around inside of this circuit and pick up my earth ground coming back through the chassis, back through the AC power mains and whatnot. For audio level signals, not a big deal. You may pick up a little hum along the way, but nothing considerable to worry about. RF frequencies, it's a whole different ball game. But now I would be able to probe around inside of here safely at this point without using one of these little clip-on things. A couple things. One, make sure your probe, if you have one and this little lead goes on there, that there's no way your finger can touch that little lead, because if you accidentally clip this onto something other than ground, and then your finger got a hold of that. And a lot of older scope probes, you didn't have this big bump up right here, and so people would put tape around them. But the problem with using one of these, and I'll just demonstrate here, let's say I clip on right here. Well, then I'm limited in where I can go inside the scope. So I'm constantly having to disconnect this thing and move it around. And I'll tell you, the more times you put hands inside of this unit and touch things, the more chance you have, of potentially touching the wrong thing. So at any rate, I like one hand, one probe like this, and we can then search around inside of here and test things. All right. Remember earlier I mentioned isolation transformer. Well, this is the one from underneath my bench. It's an old RCA, and I've had this thing in use for multiple decades at this point. And what I do is I plug this into a wall outlet, and if you'll notice, it is not tied to, and there's no ground plug to it, which means that there's no ground plug here. So I have to use a little adapter. And I don't want to do that with my oscilloscope. If you'll remember, I want to keep my oscilloscope grounded and separate. I just want to do that with my device under test. Now, I don't have to on this scenario because the chassis ground and earth ground are tied to the same. But if they had not been, then you might want to use an isolation transformer. And honestly, it's not a bad idea to use an isolation transformer on device under test all the time. The reason being, remember that conversation we had earlier about if you hold it with your left hand and you get down in here with your right hand? Well, then you're isolating the chassis the entire time, right? And what it means then is you can't complete that circuit back through your body, back down and out, because you've got this isolation transformer in play. Okay, now that I have the isolation transformer in play on this, I really have two options then, right? One, some scopes have a place for you to plug in like this, and then I can simply just connect onto signal ground here with a wire. Then I can go probe down in here, and I've only got 3 feet then of ground versus going back through the house mains and all around and back down. Works out pretty well. The other option would be is I could skip this if say it's a newer digital scope and it didn't have an input like that, you know, and then I could go back to the little scenario here of just clipping on a little lead onto ground and then testing wherever I want to test. For today's purposes, I'm going to go here with tying this to the earth ground here in our amplifier. Okay, one other thing you'll notice here is I run everything I do device under test up here through a variac, okay, and you can see I'm at 118 volts. I'll get it up to 120 volts or whatnot right here, okay? A little touchy today. But, and I need you to understand, a variac, it's an auto transformer. It is not an isolation transformer. So, you know, I run into people from time to time and they'll say, well, hey, I've got me an isolation transformer in place and I'm using my variac to do that. It is not. This does not isolate ground. It does not do, doesn't isolate the neutral the way you would need here for these purposes. Okay, I thought we'd just go through this amplifier, same one I walked you through earlier in the video, and show you how if you learn to test the right places, you don't have to worry about this high voltage, okay? So right here on the plate of this tube, the signal is going to come into it. If I want to read on one side of this, or if I want to go into the grid of this first tube right here, that would be okay. Let's do that. Okay, we've clipped onto it here. Remember, notice I did it with one hand here, kept the other hand away. Nice sine wave I'm feeding in, 0.484 volts right here. So right at line level, feeding into that spot right there, okay, right? If I want to move away from that then, and move on the other side of this first tube, what I want to do is I want to get on the other side of this capacitor right here, not this side of the capacitor, and I'll show you both and why. Alright, this is the coupling capacitor we're talking about right here. So if I come over here and clip on the left side of it, you notice I'm getting some voltage here, but I'm clipped onto AC coupling, all right? Well, because my oscilloscope, because where I'm at in the circuit doesn't have over 400 volts in it, this AC coupling is able to remove the DC component, and I'm okay actually here measuring at this point right here. If I flip this over to DC coupling, watch this. It just flies off the screen. Ouch, too many volts. I'll do bad things to my oscilloscope that way. But if I had simply went on the other side here of that coupling capacitor, okay, oops, there we go. Now I've got this signal coming out of it, but even if I go to DC, the signal's still there. Why? Because I don't have that DC component on the other side of this capacitor. Let's take another look here. I've got my multimeter on, and I'm going to go to one side of that capacitor. 138 volts sitting right there. Well, I don't really want to play around with that. If I just want to measure the signal, go to the other side of the capacitor here. Look, 0 volts basically on the other side of that, but my AC signal is still there. Alright, I'm just going to finish walking you through the circuit here in various places. Oops. Okay, right there, you notice I'm running at 6 volts peak to peak right here. Same as over in this place right here. And then if I want to come all the way over here and jump on to the actual grids here, of the output tubes. You can see here, that's about what we're feeding in right now. And because this is an 807 tube, it's kind of hard to measure the plate because it's on the plate cap on the top of the tube, which then feeds straight down in this blue wire into the transformer. But I can just simply come to the other side of the transformer, and this is on my outputs going to my speaker terminals. So that's about what I'm feeding, 11 volts or so out to my speaker terminals. But you can see I've walked the entire audio circuit from one end to the other and never played with any high voltages throughout this amplifier. Now, there are some high voltages in here, and we're better off, if we want to play with them, doing one of two things. Using a multimeter to come along and kind of measure voltage. Right there's 295 volts. Right there is 328 volts. Right back here is 396 volts. You know, I could play around and measure voltages. By the way, you can also flip this over on AC, and on that 396 volts, I can see that I have roughly 40-50 millivolts of ripple there. Now, using a digital multimeter on AC for 60 hertz is not bad. What you have a hard time seeing is if you have some higher components, maybe 1,000 hertz or 10,000 hertz signal on this, that you might be able to pick up with an oscilloscope. But if we want to go measuring things like ripple on our power supply and things of that nature, we are better off using a differential scope and probe, and we'll show you that real quick. Okay, we're over on our digital oscilloscope. Just a couple things I'd point out to you. On it, it has two ground places here to connect to. One is earth ground and one is the chassis ground here on this unit. So if you did want to clip on and do like I had done earlier, you've got a place to do that. It just doesn't have a banana jack to plug into here. Second up, I have got plugged into it my, this is a Micsig DP113. These are about 150 bucks or so. I've got another older McRae that I've used for years, but it's about had it. The cords are dry rotted and whatnot, so I picked this one up a while back. But at any rate, I've chosen to use an alligator type clip here for the ground and then just a regular probe. But it comes with all sorts of different types of connections you could use to probe with. If you'll notice here on the front of it, 50x and 500x. That's a good bit of voltage division there when you're going into your oscilloscope. But I'll show you how we'll work with that. And if you'll notice here, it also says 1300 volts input max, but for Cat 2 safety levels, it can handle 1000 volts between the two probes here. So we can definitely get in here and probe around in our power supply with no worries. Now, the way this unit plugs in, you come out one side, you go here into the oscilloscope, and I just happen to go into channel 2 because I like the blue line better than the yellow line, and it's just that simple. The other side of this, I plugged into the oscilloscope. Now, if I was going into the 2246, I would have to find something on the other side of this, a wall wart or whatnot, to plug in my, to pick up my USB power. But you can see here, you don't have as long a cords to work with, a little bit clunky, whatnot. I'm just going to clip on here onto my earth ground, and then I've kind of got this lead, and I can move around and test within my circuit. Okay, what I did is I actually clipped on using this little lead that came in the same kit. You just unplug the other unit, plug this in, and then I'm clipping onto the grid here of the 807 output tube. Okay, we've got a nice little signal here, and if I go down and read this signal, it is 178 millivolts here at 1 kilohertz. And wow, that's a teeny little signal. Why on the grid of my output tube do I only have 178 millivolts? I know there's probably more like 8-10 volts going into that tube. It's because this unit here is a times 50 probe, okay? Well, there's an easy fix for that on a digital oscilloscope. You can come over here to the probe button, and if you'll notice, you have many options here, and I can scroll down to 50x and click that on. All of a sudden now what it's telling me is volts peak to peak. I've got 9 volts feeding in. I can tell you now, up on the 2246, I would have had to done that 50 times math myself. it would not have done it for you. So that's one of the nice features of a little digital oscilloscope. Besides that, these things are super small, compact. You got your USB feed. I mean, and I paid $328 for this unit right here when I bought it new, and it came with 2 scope probes. How do you go wrong with that? Okay, but you can see here now we can get inside of this unit now, and you know, with just one hand here, get down in and clip on. Oh, look at there. So I'm clipped onto a place here where I know there's about 400 and some volts. But I'm AC coupled, and guess what? I've got a differential probe here, and I'm telling it I've got on times 50 here. So we should be able to kind of play around and start to see the little bit of noise, teeny little bit of noise. And if you'll notice, the noise here is bouncing around way up around 20 kilohertz. So I've got a little bit of high frequency on my B plus there, and way down around 100 or 120 millivolts down here. So these things do come in handy and can help you out here in what you're measuring. And what it's telling me is I might want to switch over to 500 here, and then I would change this probe over and drop it down to the 500 point here, and you can start to see some of this noise a little bit, maybe even start to diagnose a little bit of it. If I could get it to trigger well, but it's way on up in the 15, 16 kilohertz range that this noise is coming in at it. So anyway, hopefully this helps you understand a little bit how you could use a differential probe, how you can use a normal oscilloscope and work inside of one of these units very, very safely without a lot of problem. We will show you in the next video how to use your oscilloscopes. That's not what this one was about. This was about safety. Keep that one hand out. I do like having an amplifier mount. That way you're not having to be the one to kind of sturdy the unit with your left hand and have this thing mounted in here. These wood mounts are only like, I don't remember, 100, 150 bucks, something like that. All right. Thanks, everyone. Hope you learned something here today. If you got any questions, post them. I'll try to answer down below, but I think I've covered most of the basics here today.